Hello, dear candidates. Good afternoon once more, and welcome to Maths 24 Super Channel and the GCE Math Panel. In this particular lesson of the Pure Maths A-Level series, we present to you periodic functions, and this chapter is chapter 6a. In chapter 6b, we are going to be looking at how these periodic functions are sketched. I implore your indulgence to watch this video to the end so that you grasp all the concepts as they appear, and equally to subscribe so that in case you upload any of our lessons, you will be notified immediately. For complete lessons, you can visit our blog on GCE Math Panel Classes Online, where you can have all of these lessons in PDF and other forms. Stay tuned and share this video. Don't forget to subscribe. We start by looking at what are periodic functions. And a function f of t is periodic if the function has values that repeat at regular intervals of the independent variable. So a function f of t is periodic if the function values repeat at regular intervals of the independent variable. This regular interval is referred to as the period of the function denoted t. For example, we have this periodic function here, and you can see that this first line repeats, it repeats twice. So this curve repeats, and the curves are the same except that we have a horizontal shift. Therefore, each of these curves represents the period of this function, which is length along the x-axis. So this is an example of a periodic function which has been sketched, and the period is indicated as shown. The most obvious example of these periodic functions are the trigonometric functions, that is the sine, the cosine, and the tangent functions, which we have seen in the previous classes. These are most obvious examples of these periodic functions. And for these periodic functions, the sine function and the cosine function both have a period of 2 pi. The period of the sine function and the period of the cosine function are both 2 pi. That's for the normal sine t and cos t, or sine x and cos x. However, if the values are moderated, or we have coefficients like sine 3x, the period will vary given the value that is in front of delta x. Not equally that if we use the tangent function, the period of the tangent function is pi. So if t is the period for the sine function or the cosine function, then f of t plus the period, or f of t plus multiples of the period, will be equal to f of t. This is a characteristic of periodic functions. So f of any value plus multiples of the period or the period itself will be equal to f of t itself. So if instead you prove that the function is periodic, that f of t plus, let me say lambda is periodic, you just have to prove that f of t plus lambda is equal to f of t. Thus, sine x plus 2 pi is equal to sine x. Why? Because 2 pi is the period of the sine function. So sine x plus 2 pi is equal to sine x. As you can see, if our x is equal to 0 degree, 0 plus 2 pi, that will still be 2 pi, arrive at this point. So the points are going to be the same. This is for a periodic function. And equally, if the value of the sine is let me say pi on 2 at this point, which is 90. Left for the cosine, rather, for the cosine, for example, if it's 90, because 90 is 0. 90 plus 2 pi, that is a pi on 2 plus 2 pi, and that's going to give us 2.5 pi, and it occupies this position here, because this is 2 pi, right? And this is 2.5 pi, or 2.5 pi. The values of the cosine will equally be the same. So this is what we have the sine and cosine functions. But note that with the sine functions, it begins when x equals to 0 is maximum, or when t equals 0 is maximum. However, for the sine function, when t is equal to 0, it is also it's minimum as well. This is the sine function. It begins at minimum. That's at the origin. It begins at minimum. While for the cosine function at the origin, it begins at maximum. So the same thing, so cos t plus 2 pi will be equal to cos t. Note that the period of the sine and the cosine functions are both 2 pi. A function can equally be defined with its period given the form of a fundamental interval. That means the function can be defined for x, values of x from a to b, values from b to c, c to d, and so. So a periodic function may also be defined within a fundamental interval and stating its period. This is mostly for non-trigonometric functions. For example, you have f of x is equal to this fundamental interval is defined for 9 minus x squared. They're going to give us a value here, and we have 3x minus 1. These are intervals. So for a certain interval, we are going to use this sub part of this function, and for another interval, we are going to use 3x minus 1. So let us give the intervals for this function. So from x ranging from 0 to 2, that is x greater than 0 and less than or equal to 2, we use the function 9 minus x squared for this f of x, this part of the function. And for another interval, 3x minus 1, we are going to use the values of x greater than 2 and less than or equal to 4. So this function has been defined with a fundamental interval. And to obtain the period of this function, we are going to look at the lowest value for this interval for which it has been defined. From 0 to 2, the lowest value is 0 and the highest value is 4. So the period is a difference between these values. So here, the period is given by t equals 4. So 4 minus 0 is 4. And equally, if you have any function of the form g of x is equal to x for these given values, which I am going to give for the values, let me say x ranging from 1 to 4, and g of x equal to x squared minus 1 from x equals 4 to x equals 7, then the period of this function can equally be given as the lowest value here is 1 in this first interval, and the highest value in the other interval is 7. Therefore, the period of this function will be given by 6. And why is it 6? It's 6 because it's 7 minus 1. So that gives us 6. That's the period of this function, which therefore means if I'm to sketch this function, let me say, sketch this function from 0 to 10. You can start in these intervals. There is no 0 here and there is no 10. I can just sketch from 1 to 7. Then I copy and paste because the periodic function is going to be repeating as the values of x are increasing. We are going to see that in the next subchapter, that's chapter 6b, which deals with the sketching itself. Here we are focused on the characteristics of these periodic functions. So in general, if f of x is equal to, is broken down into these subfunctions, g of x and h of x, which are defined with the following intervals. G is defined from a to b, and h of x is defined from b to c. Then the period of this function in general will be given by t equals c minus a. That is the upper value minus the lower value. That's what's going to give us period of this function. Let's take some examples. So for non-trigonometric functions, the value can be determined by looking for the interval in which x value is found. So for the numerical value of a non-trigonometric function, we are going to look for the interval in which the x is found, because the trigonometric functions or non-trigonometric functions which are defined with interval notations, we have sub-functions building up that function. So if they ask for a numerical value, you have to look for the sub-function and the interval in which that value is found. Let's take an example and explain this better. For example, given the function f below, find that's f of x is equal to 9 minus x squared. We have the other parts. This one is defined from 0 to 2, and we have 3x minus 1 defined from 2 to 4 inclusive. Now I want us to find the following values. Find f of 1, f of 2, f of 3, f of 4. And so how do we do this? The first thing I have to do here is to look for this x value of 1. In which of these intervals is it found? The first interval or the second? We start 1 lies in the interval from 0 to 2. Note that with these functions, even though 0 is not included in this interval, if you are asked to use for f of to look for f of 0, you still use this function. The only difference will arise when you are sketching. When you are sketching, this value at x equals 0 is not going to be shaded. So take note about that. We are going to see that in the next sub chapter. So we see that f of 1, the value of x equals 1 is found in this first interval. So f of 1 will be equal to 9. So that's going to be equal to 9 minus 1 squared. 9 minus 1 squared because it's in this first interval. And that gives us a value of 8, right? All right, so that gives us 8. Then f of 2, if you look very well, that 2 occurs twice. It will be preferable to use the first one because 2 is included in the boundary. So f of 2 will be equal to 9 minus 2 squared, that's 5. Then f of 3, if you look at 3, 3 is found in the second interval. Although with f of 2, if you use this interval, the first or the second, you're going to have the same values to this function. But the emphasis here is that you are going to have other functions defined in fundamental intervals like this, in which the value of f of 2 using the first interval is not going to give you the same answer as that of f of 3. So when they ask for f of 2, always use the one for which the equal to sign is included. Then see f of 3, 3 is found in the second interval. So we are going to use f of 3 is going to be equal to 3 into 3 minus 1. And that gives us 8, right? The second interval. And f of 4, for f of 4, we use the second interval as well. F of 4 will be equal to 4, 3 into 4 minus 1. And that gives us 11. Okay, now there's some questions that will come now to mind, because what if you have a case where they ask you to look for something like f of 11 or f of minus 4, f of minus 10, and all those things? What am I going to do with this function? Because if you look at the definition here, x ranges from 0 to 2 and from 2 to 4. We don't have any minus 4 there or minus 5, and we don't have any x equals 11. So what if they ask me to use these functions and find f of 11 or f of minus 9? What do we do with intervals that lie outside the interval of the period? So let's see what we do in such cases, since these are periodic functions and there's always going to be a way. So if k is not in the fundamental interval, that is look for f of k, that is if f of k is not possible, then we are going to repeatedly add or repeatedly subtract the period to k until a number of value is found in this fundamental interval. So we are either going to add or subtract. We add when this value of k, f of k, let me say k is negative 11. We add until we have a value. But if the number is above, we are going to continue to subtract the period until we have a value in that interval. Let's take this example and explain it better. All right, let me just keep this one. For example, given the function f below, find, so we have f of x equals 9 minus x squared. It's the same function we have behind. So find f of 11, find f of minus 15, find f of 8 and f of minus 12. So this brings us to what we have been discussing about f of 11. When you look at the values of x here, it ranges from x equals 0 to 4, and there is nothing there like 11. So how do I find f of 11? This is what is being explained in the first case here. In the first case, if k is above, that means the value of this x you are looking for is higher than this 4 in this fundamental interval, because the highest value here is 4. Then we are going to subtract multiples of the period. The period here is 4. We'll subtract multiples of 4 until we have a value in this interval. So f of 11 will be equal to, we'll say 11 minus the period minus 4. That will give us f of 7. 7 is not found in this interval still. So 7 minus 4 again, 3. Now 3 is found in this interval. So f of 11 is the same as f of 3. So we have subtracted the period 2 times. Therefore, f of 11 is the same as 3 plus 2 times the period, which is 4. And this just be the same as f of 3. And f of 3 is in the second interval. So this will be equal to 3 into 3 minus 1. That gives us 8. Beautiful. Now the next one we have being f of minus 15. Now in the case of minus 15, we don't have any value of x defined in this interval that is negative. So we see that this negative 15 is below this interval. This is what the second point is explaining. So if the value of k is below, we will continuously add the period until we have a value in this fundamental interval. So what we're going to say is we have minus 15 plus 4, it's minus 11. It's not still found here. Minus 11 plus 4, minus 7 is not still found here. Minus 7 plus 4, minus 3, it's not still found. Minus 3 plus 4 is plus 1. 1 is found in this interval, right? So it therefore means that f of minus 15 is the same as f of plus 1. So it's just the same as 1 minus 4 times the period, right? But all these ones of multiples of the period, as we saw in the definition, this will just be the same as f of 1. And f of 1 is going to be 9 minus 1 squared. And that gives us a value of 8. Now let's look at f of 8. F of 8, let me take f of plus 15 first. So f of this will give us, all right, this is actually 4, f of 8 rather. There's an adjustment here. So we take this as f of what? F of 4, thank you. So this is f of 8. So f of 8 is the same as f of 4 plus 4. F of 8 is the same as 4 plus 4 because f of 8 is above, so we subtract the period once. When we subtract this period, 8 minus 4 is 4, right? And 4 is found in this interval. So we stop. In this case, we have subtracted the period just once. So this will give us f of 4, which is equal to 3 times 4 minus 1, which is 11. Now, one of the cases of f of minus 12. Minus 12 is below this interval. So what do? Since it's below, we do addition as explained here. It's below, we add multiples of the period until we get to something in this interval. So we say minus 12 plus 4 is minus 8. Minus 8 is not found here. Plus 4. Minus 4 is minus 4 is not found here. Plus 4 again. 0. 0 found here? Yes. So we stop. So f of minus 12 is the same as 0 plus 3 times the period, right? Yeah, 0 plus 3 times the period. Or minus 3 times the period, rather, it's going to give us the same value, f of 0. So this will be equal to f of 0, and f of 0 will use the first part of the function. 9 minus 0 squared, as we explained before, though 0 is not included in this, but this is what we're going to use. The only difference, as I've mentioned, is when we are going to be sketching, that this point at x equals 0 is not going to be shaded. Okay. Now, there's something very important that we have to note. If you look at this very well, the period is 4, but f of 8 is not equal to f of minus 8. Let's just look at this function. F of 8, from the f of 8 you have here is equal to 11, right? Now, let's look for f of minus 8. F of minus 8 will be f plus minus 8 plus 4, minus 4. F of minus 4, minus 4. So we have to add 4 again, f of 0. So it's that f of, we have 0 here, so we stop there. So f of minus 8 is equal to f of 0. But f of plus 8 is instead equal to f of 4. You have to be very careful with this. F of 0, you have 9 as answer, but f of 4, you have 11 as answer. So according to this remark, we start, for example, to f of negative 12, you subtract the period 3 times, you arrive at 0. F of plus 12, you have to just, in the case of minus 12, you add 3 times, you arrive at 0. In the case of plus 12, you subtract just twice, you arrive at 4. So it depends if the value is above or below the period. Though 0 is not in the interval, we still use that interval for f of 0. And when sketching, the value f of 0 is not shaded, as you will see shortly. Okay. So we continue. So example number 3, find the value of k below, given that g of 9 is equal to 13. So that's the function. We want us to find the value of k given that g of 9 is equal to 13. So this function, we first of all start by, if you look at this g of 9, there is no 9 inside this domain or inside this period. There is no 9. The smallest value here is 8. Or the highest value here is 8. There is no 9. So first of all, start by looking for the period. The period of this function is going to be 8 minus 1. The period is 8 minus 1. And that gives us 7. That's 7, right? Yeah. And since 9 is above this interval, what do we do to obtain g of 9? You just subtract the period from 9. So g of 9 will be equal to g of 2 plus 7. But 7 is the period. So this is just going to be equal to g of 2. And from here, this 2 is in this first interval where the k, the unknown, is also found. So it therefore means from here down that g of 9 is equal to g of 2. Therefore, at this point, we say that g of 2 is equal to 13 because g of 9 and g of 2 are the same. So g of 2 should be equal to 13, and we substitute 2 in this interval. We have k minus 2 into 2 should be equal to 13, and k should be equal to 13 plus 4, which is equal to 17. So k is equal to 17. Another example 4. Find the value of a below, given that g of 3 is equal to 5 for this function. So g of 3 is equal to 5. Now this one is direct because you can see our g of 3 here. This in this second interval, you can find the value of a directly. This 3 is in this interval. So we just say g of 3 is equal to 5 implies this a times 3, that is 3 times a minus 1 should be equal to 5. And a is equal to 2. So a is equal to 2. That's what we have. Okay, we can now look at period of trigonometric functions. At the start of this lesson, we make mention of the fact that for periodic functions, sine, cosine, and tangent, the sine function has a period of 2 pi. The cosine function has a period of 2 pi, while the tangent has a period of pi. So for trigonometric functions, the periods of sine x, cos x, and tan x are respectively 2 pi, 2 pi, and pi. In general, for sine and cosine functions represented as f of x equals a sine bx plus c plus d, as you can see on the screen, the period is given by, so if they give you a function like this and they ask you whether it's a sine bx plus c, or a cos, if it's a sine or the cosine function, when you replace one by sine or cos, to get the period, we only look at the core. After the sine, we have something bx, this bx that we have here. The period of this function is given by 2 pi, the normal period of the sine function, divided by the coefficient of x. That's the absolute value of the coefficient of x. So 2 pi divided by the absolute value of the coefficient of x, and that coefficient of x here is b. So this one is the same too for the sine and cosine functions, where in this function, a here is the amplitude, which is the maximum displacement from rest. That means you start measuring from the line y equals 0, upwards or downwards. And c is the horizontal shift. This one is a horizontal shift. Now d is the vertical shift. This value of z helps us to shift the function upwards or downwards. We are going to see some examples here. So here, like this, is it being shown? This is the amplitude of the function. This is also the amplitude. And this is the period of the function. Can equally consider this upwards to be the period of the function. And the shift is just like shifting this curve to the right or to the left along the x-axis. While a vertical shift is pushing this curve upwards or downwards along the y-axis. That's a vertical shift. So D represents this vertical shift, shifting this function upwards or downwards, while C is the horizontal shift, shifting this function to the right or to the left. So for the tan function, the period is given by a different, similar formula like this, but we are just going to erase 2 from this formula. So the tangent function, the period is given by f of x equals a tan bx plus c, implies the period is equal to pi over the absolute value of b. Pi over the absolute value of b. And for the tan function, this a here does not actually represent the amplitude, because the tan function, the highest value is infinity and the lowest value is negative infinity. So for the tan function, therefore, it has no amplitude. If amplitude is infinity, infinity is not a number. So it has no amplitude. So let's take some examples for this. For these functions given, find the periods and the amplitudes of these functions to find the periods and amplitudes. The first one, we have the period is going to be given by 2 pi divided by 5, but that's the coefficient of x. And the amplitude of this sine function is 3. The amplitude is 3 and the period is 2 pi on 5. Then for the second one, it's a cosine function, the same formula. The amplitude is 2, forget about the negative sign. And the period is equal to 2 pi divided by equation of x, which is 4. 2 pi on 4, that's pi on 2. The shift for this first one is pi on 3, while the shift for the second function is pi on 6, right? Yes, these ones are called the horizontal shift. There's no vertical shift here. And then for h of x, the sine function, equation of x here is 1, so the period is just 2 pi divided by 1, which is 2 pi. And the amplitude is 1 also. So here the amplitude is 1. All right, so here the amplitude is 1 and the period is 2 pi's. Sorry about this. The amplitude is 1. Amplitude is 1. Amplitude is 1. And the period is equal to 2 pi's. Then for the tan function that follows, the tan function, somebody can say the amplitude is infinity. Yeah, or it has no amplitude. The period of the function is pi divided by equation of x, that is pi divided by 2. It has a horizontal shift of +3. This h of x had a horizontal shift of, a vertical shift of -1, while this has a vertical shift of +3 upwards. And then the last one is a tan function. The amplitude is infinity, or it has no amplitude. And the period is pi divided by equation of x here, absolute value of this. So it's pi divided by 3. And that gives us pi on 3. That gives us pi on 3. So normally with the tan function, it has no amplitude. All right, guys, I have some exercises here for you to master, to strengthen the concept if you have already mastered. Please answer these questions and don't forget to subscribe and share these videos and leave your comments. You can join us for our live classes by visiting our blog on GCE Math Panel Classes Online or www.gcemathpanel.com. And you have a lot of materials. For past questions, go to our blog www.gcemathpanel.blogspot.com. Our next lesson is on sketching these periodic functions. Stay tuned. It was nice having you. And don't forget to share your comments. Stay tuned and bye.